Okay. And now we're going to continue by studying linear systems. So linear systems certainly are usually the first thing that we learn about when we learn any part of systems theory, be it dynamical systems or control theory, even in partial differential equations. Very often what we start with is linear systems. So this is going to be no difference. We're going to develop concepts that are familiar from linear systems, but also have a meaning in the Koopman operator theory. So how do we obtain linear systems? Well, that's a larger topic. I mean, I have just shown you a nonlinear system for which we could obtain a global linearization using an eigenfunction. You could argue that anytime I can find something like that, so in particular a mapping or some set of functions that render the system linear, that the system is essentially linear. We're just looking at it with a different set of observables that perhaps render it nonlinear. But a very common technique in engineering and science is to linearize the dynamics close to an attractor. And if that attractor is a fixed point, then the resulting system has a pure linear form with an associated linear matrix. So we'll study the general context of linear time invariant systems, so autonomous. From a perspective of spectral operator theory, really to build intuition and to understand how these concepts play out in the arena where we know the solution explicitly and we have a lot of intuition about how these systems behave. There are a number of interesting things that come out, even though the linear systems themselves are familiar to all of us that study dynamical systems, and were familiar even before applying any concepts from Koopman operator theory. But for example, the classical solution, a spectral solution of linear ordinary differential equations, turns out to contain terms that are eigenfunctions of the Koopman operator. We can define new geometrical objects to understand some of the behavior of the linear systems called isostables. I just mentioned them, and these are useful in understanding the fast and slow timescales of the dynamics. So they're very often parts of the dynamical system with certain observables that very quickly settle to some equilibrium values, and then there are some other observables or states that continue evolving over a longer time and settle to equilibrium over a longer time. So these fast and slow time scales of the dynamics can be understood in terms of this concept of isostables that comes directly from understanding level sets of specific Koopman eigenfunctions of linear systems. And then we've all learned the concepts of stable, unstable, and center subspaces. What is interesting, what's going to come out is we're going to redefine them. Usually we define them in terms of the underlying eigenvectors of the linear system. Here we are going to redefine them as level sets of Koopman operator eigenfunctions. So let's start. So we'll start with a linear ordinary differential equation in Rn. X dot is equal to Ax. A is an n by n matrix. And the solution of this equation reads x of t is e to the at x0, where I have defined e to the at here exponent as that series in the introductory lectures. Now this is of course a formal solution. It's simple to plug this solution in and find out that it really works. Utilizing e to the at as this sum. but we're going to look for a little bit more. So we did discuss this sum and the consequences in the operator theoretic context here, but we'll look for something more. The reason being that in this sum here, this is time, this is the matrix to the kth power, and this is k factorial. So as time grows large and k is large, you get some very large terms there. And obviously for the convergence, you would have to have certain cancellation of these types of terms, and so it becomes a little bit unwieldy. So it might be quite useful for short times and solving all these types of sums. If you remember, in the nonlinear case, we derived using operator theoretic methods the so-called Lie series, which in which A is the generator of the Koopman operator evolution. So it might be valuable for short time, but for long time evolution, it might become hard to see how exactly this is useful. Now, let's define. You're used to the concept of the inner product. We're going to need just a small modulation of that, because remember, we are working with complex observables. So we're going to need the definition of complex inner product. And if x and y are two complex vectors, then the complex inner product is the sum over I xi dotted with yic, where xi is the ith component of the vector x, and this is the complex conjugation. So that's the difference. That's the difference. You can again find the properties of the complex inner product defined in this form in the appendix notes. Now, we claim that the eigenfunctions that the Koopman operator associated with this linear system are simple and given by the complex inner product of x with the jth eigenvector of the adjoint A star. We didn't order these eigenvectors in any particular way, just W1, W2, W3, and so on. But they satisfy A star Wj is lambda j c Wj. This complex conjugation is due to the fact that A Vj, which would be the basis provided by eigenvectors, is dual to the basis Wj. So you have eigenvectors and dual eigenvectors that are really eigenvectors of the adjoint A star. I should mention, because I don't think I did, is that in this, we are going to be working with, first with a situation where A has simple distinct eigenvalues, and it has, it has n distinct eigenvalues and eigenvectors. But we will soon expand that to encompass the situations in which it might not have eigenvectors, but has generalized eigenvectors. Okay, so one of the things I'd like to point out is that the matrix A, the eigenvectors of the matrix A Vj, and the dual eigenvectors Wk, which are the eigenvectors of the adjoint, they can be normalized so that the complex inner product between Vj and Wk is delta Jk, and that's a Kronecker delta that is 0 for j different than k, and it is 1 for j equal to k. And so far so good. Let's take this function. It's a linear function in x, right? It's an inner product between complex inner product between x and Wj. And so let's prove that that's actually an eigenfunction of this equation here. So the proof is easy. You take phi j dot, that's an inner product of x dot and Wj. X dot is ax from here. And then we are going to use the adjoint. The adjoint, of course, just takes A to the other side, and we take a adjoint that is denoted by this star over here. So we have inner product between x and A star Wj. which is equal, of course, to AX WJ inner product. And so now that, by this equation here, is just lambda JC WJ. So I would have to put lambda JC WJ over here. But lambda JC is a scalar, complex scalar. And it's the property of the complex inner product that when I have the complex conjugate scalar in the second argument here, that comes out of the inner product as its own complex conjugate. So since I have lambda JC, the complex conjugate of that is lambda J itself. So that's lambda J. This thing was defined to be, or rather suggested to be an eigenfunction. So that's lambda J phi J, and I get my equation. Phi J dot is lambda J phi J, and I just proved that this linear function here is indeed an eigenfunction of the Koopman operator associated with the eigenvalue lambda J. In other words, Koopman eigenfunctions for this linear system are complex inner products between X and the left eigenvectors of A, or rather the eigenvectors of the adjoint. So now in our notation that says, phi J of X is a function of X itself, and that's kind of a static function. But if we wanted to know how it evolves in time at any point x0, then that's defined to be the evolution under the Koopman operator of Fj, of this static function here. And that is obtained by just solving phi j dot is lambda j phi j, that is e to the lambda jt phi j of x0. So that's how the eigenfunction evolves at any x0 for any time t. Okay, so now we know what the eigenfunctions, at least some of the eigenfunctions, look like. And so for any x in the state space M, which is for us, we can take it to be Rn. As long as A has a full set of eigenvectors at distinct eigenvalues lambda j, we can write any x in that space as a sum of inner product between x and wj and vj. So this is the property of the dual basis. We have the eigenvectors vj, those are v1, v2, to vn. So that's our eigenvector basis, and note that it's a complex basis, but I can represent any real vector in that complex basis by inner producting that real vector with w1, which is the eigenvector of the adjoint, w2 to wn. And remember that I'm using dashed lines on the bottom here for boldface quantities. So any vector can be expanded in terms of eigenvectors vj by basically projecting or getting the quote unquote coefficient of x in the direction of vj by inner producting it with wj to get a kind of a sense of how this works. Let's say this is v1. And this is v2, and let's say everything is real, then orthogonal to v2 it had a w2, and orthogonal to v2 I'll have w1. I'm sorry, use this. And orthogonal to v1, I'll have a w2. And so the inner product between w2 and v2 is non-zero, but the inner product between w2 and v1 is 0. The inner product between w1 and v2 is 0, and the inner product between w1 and v1 is non-zero. And if I wanted to get these coefficients that I'm interested in, I would basically, the idea is that whatever vector x I have, the coefficients that I will get by just moving this vector v2 parallel over here, and that would be the associated coefficient that I would get. So that's a little bit of geometry. As I said, you have the full explanation in the appendix, or if you pick up pretty much any book with a bit more advanced linear algebra, it will talk about these types of dual bases. So now let's take x as a function of this boldface x0, which you can think of as a vector in Rn, be a function such that it associates with any x0. The jth element of that vector function is xj, the jth Cartesian coordinate associated with x0. So that's xj0. So where x0 has components x10 to xn0. Yeah. So let's now do a computation. The evolution of the Koopman operator applied to this vector of functions x0, or rather, that's by definition just capital X t x0. Now that's e to the at x0, right? It's remember the Koopman operator composes x itself with the evolution, and the evolution is e to the at, and that's evaluated at x0. So let's expand this vector e to the at x0 in terms of the eigenvector basis. So this is the expansion. So the first argument here is just copied over from here. That's this x. And the second is wj with vj. Let's take e to the at and conjugate it to get e to the a star t. If you conjugate e to the at, you're going to get e to the a star t, where a star is the adjoint. I'm sorry, if you adjoint the e to the at, you're going to get e to the a star t, where a star is the adjoint of a. And now we know that e to the a star t, wj, is really e to the lambda j complex conjugate. But that's in the second argument again. So when we put it out of the inner product, it ends up being e to the lambda jt. x0 wj we recognize. That's the eigenfunction of the Koopman operator at the point x0, and then vj is the eigenvector of A. And so this is an interesting result. It is in parts well known. So what we got here is really just the expansion of the e to the at x0 so that solution of the linear ordinary differential equations in terms of the eigenvalues of the matrix A, the eigenvectors, and then this function here of initial conditions. But by what I've just discussed, here is another interpretation. Lambda j, while eigenvalue of A, is also an eigenvalue of the Koopman operator. Phi j, this function of initial conditions, when I was taught linear ordinary differential equations, this was summarized as being just some function of initial conditions that can be defined. But that turns out to be an eigenfunction of the associated Koopman operator. And that's perhaps a little bit, a little surprise there. There is something in that linear expansion that is actually directly associated with the Koopman operator as a function of points in the Euclidean space. And then wj are the eigenvectors. You will see as we go that even in the nonlinear systems case, for a large class of systems that have what is called a point spectrum, this is the correct form of the expansion, except that n is going to be infinity now. in the nonlinear case. Very often it's going to be infinity in the nonlinear case. This is what we call the Koopman mode decomposition. And the modes in the general nonlinear case are reduced to eigenvectors in the linear case. So it is what we call the Koopman triple. We have lambda j, which is the Koopman eigenvalue, phi j, which is the eigenfunction, and vj, which is the eigenvectors. And the three together form the Koopman spectral triple: eigenfunction, eigenvalue, and mode. Now, two of the three are the properties of the operator. Lambda j is associated with the operator. Phi j is associated with the operator. But vj is actually not. That depends on the observable that we chose. Here we chose what are called state observables. So we just chose to observe states of evolution, x1, x2, x3, and so on. But if we chose, for example, some matrix, m by n matrix applied to the states, and called that f for some to obtain a new linear vector observable, then the expansion, so UTF, as is simple to see because I could just multiply that by C from the left and obtain CVJ here. So my quote-unquote Koopman mode, remember this is the eigenvalue, eigenfunction, mode would be really the matrix C applied to the eigenvector Vj. So again, the eigenvalues and eigenfunctions are properties of the underlying Koopman operator. They are general. The modes themselves reflect the properties of the observables. But what is nice that in the linear case, they're nothing but, if you take state observables, they're nothing but eigenvectors. In a nonlinear case, of course, there is no notion of eigenvectors, general notion of eigenvectors, because you don't have a linear system. But there is a notion of modes that directly extends the notion of eigenvectors in linear systems. And so this is the first time that we encounter these expansions. What I talked about at the beginning of this part is the fact that this might be valuable at a short time, but at longer times, these t to the k terms might be problematic. Now, if you look at the expansion of the solution that we have here, if lambda j's, for example, have negative real parts, all of these terms are going to decay in time to 0. And in that case, we would have a stable equilibrium. And so certainly that would describe the asymptotics of the solution and transient to the equilibrium really well. So that's where we're going to stop for today and continue next time with a study of linear systems with more general matrices A that don't necessarily have distinct eigenvalues, but might have repeat eigenvalues.